Welcome students to the third week of Monitoring Control, in which we look at process analysis. So another topic in the field of operations management. So what we do today is, first of all, the overall purpose of today's lecture is to examine a process from a perspective of flows. So inputs flow in, outputs flow out. So this has a very widespread application, and this is something we are going to deal with today. The first thing we're going to look at is what is a process, and there's some terminology that I'd like you to understand. What is throughput, what is cycle time, what is work in progress, and what is lead time. If you understand those, you're very far in understanding, having a first understanding of what a process actually is. Then we look at Little's law and the applications of it, and then at some types of processes. So let's start with the first one. What is a process? So let's start with the question, what is a process? And already last time in the lecture, I already gave you a kind of similar picture. So inputs are transformed into outputs. And inputs can be very, very diverse. As said last time, it can be money, it can be hours, it can be units, it can be so many things. Inside the box here, basically, the inputs are matched with, so let's say hours of employees are matched with certain materials. And in the end, you get an output, which can be units, which can be money, and so on. So a process is any part of an organization that takes inputs and transforms them into outputs. So that's very, very simple. I just wanted to use that as a starter to get you to refresh this idea. So then it's important that we look at certain key concepts. The first one is throughput, which is the average amount of units, let's say the average output per, let's say, a certain amount of time. And here we could say, let's say, if we would be a smartphone manufacturer, we could have 60 smartphones an hour that we produce. Let's say the average output per hour, so per unit time could be per hour, per minute, per day, or something like that. Then an interesting thing is cycle time, which it basically is not 60 smartphones an hour, but the question, how long does it take to get one next smartphone? So it's not smartphones per hour, but in this case, well, we have 60 smartphones an hour. This is equivalent to one smartphone a minute. So this would be the cycle time, one smartphone a minute. So cycle time is the inverse of the throughput, so 1 divided by throughput. So if you understand throughput, you can also derive the cycle time from that. Well, then we have the lead time, which is the time needed to process a part through a facility. And you might question, well, what is the difference between lead time and cycle time? Well, lead time is the whole time. So it's not the time until the next unit comes out, but it's the whole time from the beginning where the inputs are taken to the end. So the whole time that one input item takes to complete the process. But we'll come to examples of that in a minute. And then we have work in progress, also called WIP, which is the amount of units being processed at this moment. And on the next slides, we will have some examples of each one of those concepts. So then hopefully it gets a bit more clear. So let's take the example of a university. Let's take the example of Fontis. So we have prospective students. You were prospective students at one point in time. Now you're actual students. And the amount of students in that box here, so the amount of students we have on our campus is the work in progress. So what is the amount of units in the process? Your lead time is 4 years, because basically you need 4 years, hopefully only 4 years, to finish your studies. So that's the whole time. But now the question is, what is the cycle time for a student? Well, the cycle time actually is 1 semester, because every semester we are getting graduates. Every semester students finish university, so cycle time is then every semester basically. So, and the output are, of course, you as graduates. So, what is a steady process? This is now another important idea. Well, it's still inputs, transformation, outputs, but in a stable environment, the average inflow rate is equal to the average outflow rate. This simply means in a steady system, you get material or hours in, you transform them, and the same is also going out basically. So the throughput rate, this is also called the throughput rate, so how many are coming out of the system, how many units are processed per time. And the average flow rate through the system, as said, is called throughput, so the number of jobs per, let's say, hour, per minute, that is finished. And in a stable environment, throughput is equal to inflow and outflow because it's stable. So what you get in is also what you get out. And this is something that is going to be important later when we look at Little's law and the applications. Well, we also looked at cycle time before. So let's look at, this is another example, let's look at the 4 workstations that we have here. So we have a production system, we have workstation A, at which 2 hours are used to produce 1 unit. B, C, and D is the same thing. And now the question to you is, how long does it take until I can grab a new product? Well, it's 2 hours. So sometimes it's, let's say, very tempting to say it's 8 hours, but that's not the case because every 2 hours we can pick a new item. And that's what is meant with cycle time. So it's 1 item per 2 hours basically that we get out of the process here. So one more addition to the cycle time. As said before, the cycle time for Fontes as a university and getting out students is half a year. So every semester we get new students as graduates. But you might think, well, let's just take an example. Every semester 500 students graduate. Then the inverse would be the cycle time. But you would say, well, that's not always 1 semester because the throughput changes, so the cycle time must change as well. But the important thing here is that Fontes is not a typical production system. So this means in a normal production system you have a steady flow of materials, materials coming in, going out, so you can actually calculate cycle time depending on the throughput. But as a university, there are no students graduating in the middle of a semester. It's always at the end of the semester. Therefore, the formula that we showed before, of course, works for a normal production system. But if you only have certain moments in which products come out, let's say after half a year, which is of course not feasible in a normal production setting, then of course the idea still holds that a cycle time is time it takes till the next unit comes out, but you can't of course take the inverse of the throughput for a university, but just as an addition to what I have been saying before. Well, then opposed to that, as said before, lead time is looking at the total time. So from the beginning, so from raw materials being put into the workstation, finishing A, B, C, and D, and becoming a finished good. So the total time spent by a flow unit within the process boundaries. And if we now go back to that slide, well, we can say 2 hours was the cycle time, but 8 hours actually would be the lead time because it takes 8 hours for complete process to run. And this application of lead time can be used in a lot of also real life situations. If we are looking at a bank, the average time a customer spends in the bank is the lead time. So customer arrives, there's some waiting, so customers have to wait in line. The customer is being served, is processed, and then at one point in time he leaves the bank again. So the whole time is the lead time. And then we also have, of course, if you order something online, if you look at the example of Amazon, Amazon gets the books, puts them somewhere in stock. This is the storing. Then we place the order, or you place the order. The book is picked, packed, and shipped to you. And the whole process is the lead time. But of course, you only see this part from order to shipment. But of course, there's more to that than only these items. And this is some applications of the lead time. This example of a factory makes clear again what work in progress is and also what lead time is. So in a factory we get certain inflows as raw materials, they are transformed, and the total amount of units in the system is called the work in progress. What comes out is the finished product, and the total time it takes is the lead time. And the time until one more unit comes out is the cycle time. All right, and as said before, in the steady system, throughput is equal to outflow and inflow, because what we get in is what we process and get out. And this basically hopefully makes clear what the difference is between throughput, cycle time, work in progress, and also lead time. So let's now look at Little's Law. And Little's Law is actually about steady systems. So there's a long-term steady state relationship amongst inventory, which is another word for the items stored or work in progress, the throughput, and the lead time. And I said it only works for steady systems. So where you have an input, you transform it in the output, which is quite similar. So you take 5 raw materials, you actually transform them and they get out. So the inflow is equal to the outflow. And in real life, of course, like a perfectly steady system is might be hard to find, because there are always some minor fluctuations, or more or less minor fluctuations. But even then, Little's Law works, because on average, there is a steady system. But we'll discuss this in more detail now on the next slides. So Little's Law actually uses a bit of a different terminology than the terminology we have been using, but we translate Little's Law to what we have been teaching a couple of minutes ago. So the average time in a factory or facility is called W. So let's say a waiting time or something like that. Then this is equal to L, which could be something like load, divided by lambda. So now you might say, wow, this doesn't make sense. And of course, based on what we learned before, those things are confusing. So we translate them now to our terminology. So W can be seen as lead time, L can be seen as work in progress, the load, the amount of units, and lambda is the throughput, so items per hour. So if we translate that, we can actually see lead time equals work in progress divided by throughput. And this is what we can now use to start calculating and start using Little's Law. Let us now look at the first task, which looks at a factory. So the example of a factory production. So we should determine how many batteries are as work in progress for the following auto manufacturer. It needs 12 hours to make a car. So the factory needs 12 hours to make a complete car. The factory assembles 200 cars per 8-hour shift, and there's currently 1 shift working on the cars. And finally, 1 car equals 1 battery. So what are we searching for? The work in progress. Let's now look at Little's Law again. So work in progress was the L, so the amount of units in the process. So work in progress equals L. The lead time is actually 12 hours to make a car. This was called the W, the waiting time, in Little's Law's terms. And throughput, so the lambda in the terminology of Little's Law, is 200 cars per 8 hours. So this was the original law, W equals L divided by lambda. And we're searching for the L. We're not searching for the W. So what we have to do is try to let the L stand alone. And this is very easy. We just multiply the whole thing with the lambda. So we have L equal to W multiplied with lambda. And now we can solve that equation. So we said before, the work in progress, the load, the L, is equal to throughput multiplied with lead time. So work in progress equals throughput multiplied with lead time. So throughput is 200 car batteries per 8 hours. So this means 25 batteries per hour if we divide 200 by 8. Multiply with 12 hours, which is the lead time, and we can see the work in progress is actually 300 batteries. And this way we can solve the task. Let's now look at exercise part 2. So if the factory holds on average 8,000 batteries in raw material inventory, how long will it take for this stock to be depleted? So to be gone. So what we have here actually is 800 batteries, which is the work in progress. We still have a throughput of 200 batteries per 8 hours, so basically 200 batteries per day. And what we search for is the lead time, the time it takes until all the 800 batteries are gone. So in this sense, lead time, this was the original formula of Little's Law, the W equals the L divided by lambda, or lead time equals inventory, work in progress, divided by throughput. So lead time is inventory, work in progress, which is 8,000 batteries, divided by 200 batteries a day. So 200 over 8 hours, so 200 per day. And this gives us 40 days. So within 40 days, the inventory that the company had is gone, and they have to see that they ordered before that date new batteries. So let's look at applications of Little's Law. And in real life, there are a lot of applications of this law. So if you work in an office, you get certain orders in, you process the orders, and they get out, so in and out. And if you're, let's say, working concentrated on that, more or less what you get in is also what you get out. Of course, this doesn't work for the start and the end of the process. If you're, let's say, getting a coffee and then start to read, of course, this is not a steady process yet. But once this process is steady, so you're working concentrated on the task, well, it is a steady process. Well, for parking lots, it's the same. Amount of cars going out, amount of cars going in, there's a steady relationship. And also, if you look at the digital world, this example, last year I wanted to buy tickets for a concert, and this concert was very popular. So basically, I went on the website, Eventim, and they said, well, please wait a minute, and then you will be redirected. And this is also the same, like the capacity is full. Then let's say within 1 minute, one customer is finished. So cycle time, 1 minute, let's say 1 minute, one customer a minute. Of course, probably is more. And then new customers come in. So that's also steady state. And finally, also, if you put water in a water tank, what comes in could be the same as what comes out, also a steady system. And then you can calculate how much water, for example, is as work in progress, what the lead time is, and so on. So these are just some examples, but there are numerous more in real life. So, and these numerous more can also be seen here. Well, you don't have to memorize all the situations in which Little's Law actually work. If you go to the supermarket, there's a queue for the cashier. There's also a steady relationship of customers coming in, waiting, being processed, going out. If you're at a harbor and ships are being loaded, this is can also be a steady relationship. So there are way more applications. You don't have to know them all as said, but this is just as to give you an idea where Little's Law can actually be applied. Well, let's now look at the last learning goal, which is about classifying the types of processes. And there are actually two ways of doing this as a single or multi-stage process. Single stage actually means that all activities are collapsed and take part in one cycle. So this means, let's say, here in class we now had 3 learning goals, and they all take place in this class. So it's one single stage in which the activities are performed, and a multi-stage which actually has multiple groups of activities. Let's say now after this lesson you go to another lesson. They also have certain content they deliver to you, and this basically is then a group of activities, let's say this lesson, the other lesson, that do not take place in one stage, or in this case in one classroom, but in more classrooms. So you can see it here, you go from stage 1 to 2 to stage 3, which is a multi-stage process basically. And each stage, as said before, there are multiple activities that happen in one stage. Okay, let's now look at the examples of a multi-stage process. And McDonald's is a very good example because if you go through the McDrive, you order your products, then you go to the next counter, you have to pay your products, and then at the third one, you are at the second counter, you actually get your product. So that's an example of a multi-stage process. In order to describe what a process is, there is some more terminology that is important. Buffering, blocking, starving, and a bottleneck. So let's start with the first one, buffering. And buffering is very important. It actually means that you have a bit more of raw materials or resources between the different stages in the process. So let's compare it to yourself. Let's compare it to you studying for exams. Let's say you have 3 exams to write. And let's say for each of the exams you plan to study 15 hours. Then in the end, you might want to plan a little bit of time in between the studying, let's say 5 hours more in between, so that you can say, well, 15 hours was not enough, I need 2 hours more. But then you have the resources to actually study more. And this is also very important for your personal time planning. So if you have a very, very strict time planning, and then there's something unexpectedly happens, the whole time planning doesn't work anymore. So buffering is very important. Also, if you look then at factories, have a bit more raw materials than you actually plan with so that you can react to fluctuations. So a buffer is something there that we put there intentionally, so on purpose. Then we have a blocking, which actually is a very bad buffer, basically. Now you can't say it's a buffer, but it actually means when you have, let's say, a stage in the process. Let's say you produce certain car parts, you produce them and you want to put them on inventory, but there's no space to put them. You actually have to stop stage one. You have to stop the process until there's space available. And this is very bad. This is also kind of buffer, but it's a buffer that is not planned with. It's a bad buffer, you could say, because it stops the whole process. And a buffer actually is a good thing. So a planned buffer is a good thing because then you have a bit more of raw materials if you have, let's say, fluctuations. But a blocking actually means that the whole process has to stop at a certain part because you don't have space to put the raw materials. Well, this can't happen to you if you plan too much time for your exams, practicing, because you don't have to store time. But if you have to store items physically, this can happen. The opposite is starving, which actually means that there are too little resources, too little work to be done, so process have to stop because there is not that much work to do. And that's also something not planned with, unintentionally, which is not good for a process. And then the last thing is a bottleneck. So it's a stage that limits the capacity of the process. So basically the slowest part in the process, which slows everything else down. Because you can have a very, very fast part of a process. If another part is slow, well, it doesn't help you at all. So let's analyze bottlenecks. Let's try to analyze where the bottleneck is in this process. So you have 5 workstations where products go through, A, B, C, D, and E, and you see the speed of the operation. So 30 units an hour, 20, 12, 60, and 15. So that's the fastest one. And the question for you is, where's the bottleneck? And the bottleneck actually is the 12 units an hour. That's the workstation, because this actually is the slowest part of the process. And even though this is quite fast, the other ones are also faster, the whole process is slowed down, and every hour, 12 units come out. So the throughput is actually dependent on the bottleneck. So it's determined by the bottleneck. All right, let's now look at work in progress again. We've talked about this briefly before, but there is a good relationship between the 4 items we discussed before and work in progress. So work in progress is the amount of units in a system. But the important thing is, if the outflow rate, if the inflow rate exceeds the outflow rate, there's a pile up of work in progress. So more and more and more work in progress, which could lead to blocking finally. And of course, if you have, let's say, an inflow rate which is different than the outflow rate, you have an unstable system and not a stable system anymore. And classified with this symbol, you don't have to worry too much about it, just that you know this symbol represents unstable systems. Let's look at this one again here. Let's look at this system. So the question to you is, where does work in progress pile up? Where does it get more and more? First one is between A and B, because this is quite fast, 30, but it can only be processed further by 20. So there is some pile up of work in progress. The second one is here between B and C, because this is faster than this. So 20 per units per hour, and this is only 12. So per hour, on average, there might be 8 that are piling up. And then the question is, where else do we have a work in progress piled up? Question is there work in progress piling up? Unintentionally, in the original slideshow, we said yes, there is work in progress piling up. But you were clever enough to say this is not the case. So basically, we just tested you, right? There is no work in progress piling up. And the reason for this being that here, actually, this is very fast. So it's 60 units an hour that it goes through. But it can never actually, on average, achieve those 60 units an hour. Because here, 12 units an hour is the bottleneck, and actually also limits this subsequent process. Because this can never achieve the 60 because this is limited by the bottleneck. So essentially, this is also only being able to operate at 12 a unit. So it's slower than this, so there's no pileup of work in progress. So we could say that here, there could also be kind of starving happening, because this is slower than this, and it takes more and more and more, but at one point in time there might be no materials left. So let's now look at the last part of today's lecture, which is looking at processes and systems, because there's an essential difference between those. So a process could be compared to a sulky race with just one horse, and a system could be compared to a chariot race with numerous horses. So let's have a look at the first one, a sulky race. You have one horse, and in order to win the race, you have to train your horse the best. So the best trained horse wins the race. The horse that can actually run best on all the different surfaces, all the different environments, work best on all different environments, wins the race. So that's a process. The difference to systems actually is that in a system like a chariot race, you have more horses. And there, even if you have the best trained horse, if the other horses are not that well trained, the whole system actually is not as fast, because actually the slower horses slow down the fast one. So the important thing here is look at the personality, strength, preferences of the different parts in the system, so of the different horses in this example, and try to harmonize them, because actually performance of one horse influences the other horses. So that's the difference between a process and a system, and here you have to make sure that the system runs in harmony. So that's it for today. The homework is looking at Little's Law again. So first of all, Little's Law in a clinic, Little's Law in a bank, and then also think about this following question. Why would organizations with optimized production processes might still encounter deficiencies as a whole? You see a very, very fast car, but it's still slowed down. So write down or think about your ideas of this regarding this task. Thanks very much for watching, and have a good day.